Hello and welcome back to Calculus 3. So today we are going to talk about vectors. The first lecture is 13.1 vectors in plane. That means 2D. So the 2D surface. So 2D surface is going to be the xy as a point. And we have our coordinate system where we intersect x and y coordinate axes, and that's what we call Cartesian, two-dimensional Cartesian coordinate, also known as rectangular coordinate system. So all of that good stuff that you guys know from before. And now we are going to introduce mathematical concept called a vector. So this creature here is called a vector, and vector is a mathematical construct. They don't exist, just like numbers don't exist. You don't see number 7 walking down the street, so you're not going to see a vector u walking down the street. Vectors have magnitude, which is technical length in some cases, and they have direction. Which is the way they go, the orientation. So certain physical quantities in the world that surrounds us can be described only with numbers. And others would also need the direction. So the concept of velocity and the concept of a speed. So velocity is the vector, and for velocity, the direction and the size of the vector matters. Where speed is what we call scalar, is only the number, no direction. So it's kind of bad to have a speed limit. It should be a velocity limit, right? Because you should be moving in the direction. Now they say, okay, it's common sense which way you go on a highway. We all should go the same way. So, okay, fine. I'll give you that. But then see, when you talk about velocity, velocity is the speed and the direction in which you go. So magnitude of velocity is speed. And the speed is just a number. So your speedometer has no direction attached to it. It's only the amount of speed that you have. So you're going 50 miles per hour, 60 miles per hour. And don't try this on your own. Try it when someone else is driving. If someone else is to drive in reverse, the car will still show, if you go 20 miles per hour in reverse, it still shows 20 miles per hour. There are no negative numbers on your. So the direction, or the speed has no direction to it. Where velocity is the speed and the direction combined. So now, if I have a vector in the coordinate system, So if I have a if I have a vector that stretches from the origin to this point 6, 3, I can calculate the magnitude by using Pythagorean theorem, 6 squared plus 3 squared. And I can calculate the direction, which is given by the angle theta as the inverse tangent of 3 over 6, which is 1/2. So if this is my vector u, magnitude of vector u is denoted as this absolute value. And in our case, it is going to be x squared plus y squared. Direction of u is going to be theta, and that's defined as the inverse tangent of y over x. So this is what's important for vectors. Now, if you really want to know what the vector is, vector is more advanced number. You see, number, like number 7, provides you with one piece of information, which is quantity. So I can go and I can say 7 chairs, and we're done. Vector has that feature already. It's called magnitude, so quantity of 7. But it also has direction. So vectors have 2 degrees of freedom to measure concepts, which is why they're used for forces, right? You don't care that I'm swinging my arms around as long as it's away from your face, right? You don't care about the magnitude or how strong I am or anything like that. As long as the direction is not towards your face, you're fine, right? So what I just explained is the vector of force, right? And the direction and the magnitude are important because it is how the strength that you would use to strike, that would be magnitude, and obviously the direction in which you strike matters as well. So both of the components work at the same time to produce a vector, where for a number you only have quantity. So when we talk about the weight in United States, that's force. Pounds, that's force. And you weigh yourselves, and then you're either depressed or not, whatever. But the fact is that if you are to weigh yourself on the top of Mount Everest when the moon is directly above you, you are going to weigh less than if you weigh yourself in your bedroom. Frostbite contributes to that weight difference, but that's a different story. So now, if you consider mass is scalar unit measured in kilograms or grams, and mass is not dependent on gravity. So 5 kilograms on Earth is 5 kilograms on the moon, where 5 pounds on Earth is not 5 pounds on the moon, because the gravity of the moon is much less than the gravity of Earth. And the weight, which is the weight as a vector, I'll delete this, is mass times gravity. Now gravity is a vector because gravity is acceleration that points downwards at either 9.81 meters per second square or 32.2 feet per second square. So when we talk about vectors in 2D, we have to understand that the vector is mathematical construct. They don't exist, but we can use those vectors to portray a lot of physical phenomena that is happening around us. Weight, which is force, so forces, velocity, acceleration, and some other features, right? Those are all vectors. And then you have scalar quantities, which we are not considering here, like mass, time, and so on. Those just have a quantity. They do not have direction. Now, when you have a vector can be decomposed into its x and y components. If you ever took physics, I'm just wasting your time, I'm sorry, but such is life. This is my vector u, and this vector u can be decomposed into two vectors. This is uy and ux for x direction. There is still theta in here. So we can use trig to decompose these values. So your ux is going to be u times the, what I need ux, so times the cosine of theta, and uy is u sine theta. Now, oh, I forgot the absolute values here. These are, there we go. These are the magnitude, right? The hypotenuse is the magnitude. The length of the black line is the hypotenuse. It's the magnitude of, right? It's the magnitude. So the picture that I have over here is 4 and 2, and we also have, so now what I have is a vector that starts at 0, 0. We call that initial point, and ends, maybe I'll just say vector. Vector starts at 0, 0 and ends at 4, 2, which is a terminal point. So the vector will start at 0, 0 and it will end at 4, 2. Now it's important because we'll see later that if you switch and start point and end point, then the arrow goes the other way. It's important. So now I can calculate the magnitude of the vector by working out 4 squared plus 2 squared is equal to 16 plus 4 square root of 20, which is 2 root 5 units. I don't care what the units are right now. They could be units of the pounds or whatever. So my vector u has this, and we can calculate theta, which would be inverse tangent of 2 over 4, which is inverse tangent of 1/2. You switch your abacus to degrees. Your calculator should always be in radians, but you know, once in a while you have it in degrees. So inverse tangent of 1/2 is 26. It's about 26.6 degrees. So that's our vector. Oh, I never actually gave you the, wow. I never put a notation for a vector. I talked all about these things. Maybe over here, I'll say that this particular vector u is 6, 3. You use these spiky brackets. This is what I have. This is what I added to notation right now. You use the spiky brackets to denote vectors, and you just use the terminal point to describe the vector. So it's 6, 3. We can go here, call it 4, 2. So this particular vector u is 4, 2. So you list, just like listing a point, 4, 2, except you use spiky brackets, so that's the vector. Great. Now, component form. We have unit direction vectors I, which is 1, 0, and j, which is 0, 1. And we can take our vector u, which was 4, 2, and write that vector as 4i plus 2j. And that would be the component form. So if I have vector u to be given as a, b, you will have ai plus b, j. There we go. So that's our notation, whether you want it in the vector form with these brackets, or you want the component form. Now, in terms of graphing, if you are looking at the vector u equals 4i plus 2j, you will just draw those vectors. You will draw 4 i's, and then you would go 2 j's up, and that would create your vector u. So you had 4 i's and 2 j's. 4 i's and 2 j's to come up with this graph. Now, you probably studied complex numbers at some point, so you know there are complex numbers, which is a plus bi, and your professor teacher might have mentioned or might not that those were two-dimensional numbers. Well, you can treat vectors as two-dimensional numbers as well. They have two features, magnitude and direction. And now, when you put in a component form, it looks like there is a dimension for x, which is the I. Dimension for x is separated from dimension for y, which is j. So you can also think of it that way as well. So now, since vectors are like multi-dimensional numbers, we can operate on vectors, do the addition, subtraction, multiplication, scalar multiplication, and so on. So operations on vectors. I mean, I'm going to say vector operations, but whatever. So I can add two vectors. If I go u plus v, that would be vector u, I'll call that ux, uy, plus vector v, vx, vy, and then when you add them, you add x component to x component, so that's ux plus vx, comma, uy plus vy. So you add x components together and you add y components together. So that's the way to add vectors algebra. Now, yes, you can go and do the ij form if you want, the component form. It's the same thing. So now, what is the vector addition? We'll do this graphically and obviously using the formula. So say vector u is 3, negative 6, and vector v is 1 and, I don't know, 4, whatever. I can quickly add these because u plus v is simply 3 plus 1 is 4, negative 6 plus 4 is negative 2, and I am done. We're done. Right? As simple as that. Add x components, add y components, you're done. But now I would like to explore the graphical, right, method. And for that, we need to be precise. So I have my 3, negative 6. So 1, 2, 3, 1, 2, 3, 4, 5, 6. So I have the vector u. Right here. That's vector u. And then vector v is 1, 4. Now 1, 4, 1, 1, 2, 3, 4 is here. And since vectors are free to move in space, I can slide vector v down so that the initial point of vector v collides with the terminal point of vector u to give me something like this. So this is also vector v. And now, if I connect from the origin to where the arrow ended, I will have u plus v vector. And if you take a look at the coordinates for this one, because it's done on a square grid, you see that the coordinates are 4, negative 2. So we can add vectors graphically. And if you take physics and you do the force tables and all these things, you probably have already seen all of this stuff. So, as I said, I'm wasting your time, but it's first lecture, so, you know, give me that much, please. Now, subtraction doesn't exist, actually, because there's no need for it. What we what we have for subtraction is actually addition of the vector that is just flipped. Now, I will explain that after I talk about scalar multiplication. So after I finish with the scalar multiplication, let's go with the scalar multiplication. That is C times vector u. That's what I'm talking about. So Cu, I'm going to bring it closer. Give me a second. So C times vector u is C times ux uy, which is cux cuy. And to box that. And what this does is just scales your vector. You can make it longer, or you can make it shorter by multiplying it with a number. So if I have vector u, which is the, oh, by the way, this marker that I use for dry erase board is actually a vector, because the magnitude that I use to press and the direction which I turn the marker in, right, is important, otherwise it doesn't work. Because look, it doesn't really work because the direction is off. And now if I go like this and I'm barely touching, right, you can't really see that I wrote number 3, because the magnitude in terms of me pressing was not well, right? Now, but you also can say, okay, I have an object and I can add another one to it. So this is technically 1 times 2. If this is my vector u, this is my vector 2u. As I link these two markers one with the other. So if I have 2 times vector 4, 2, it becomes vector 8, 4. You just distribute and multiply each one, and you are done. All I did is I made this vector twice as long. That's all I did. I can cut it in half. 1/2 of 4, 2 is 2, 1. Half of the vector. So we can do scalar multiplication. Now, since direction is important, if you multiply by a negative number, you also flip the direction. I should write that. Let's go orange. If we multiply by a negative, we change the direction. I'll put also in parentheses as well. And the reason why I put in parentheses as well, I don't have to, maybe I don't get to change the magnitude. If I multiply by -1, right, it's still the same length, it's just flipped. That's all it is. So we have to be careful about that. So if I have a negative, let's say -3 on a vector 4, 2, it becomes -12, -6. So in this case, the direction is different, right? It's going opposite, and the vector is 3 times longer. So I hope that all of this so far is common sense. So now that I established multiplication and addition, I can now combine those two into subtraction. So subtraction is a composition of these two. So vector u minus vector v is vector u plus -1 scalar times vector v. That is your subtraction. So there is no subtraction for vectors. It's actually just scalar multiplication with a negative and then vector addition. Good. All right. Let's see. Have I missed anything other than properties? Okay, this is a good one. You'll definitely need this. To obtain a vector given 2 points, subtract the coordinates. So if I have a point P, let's say 3, 6, and I have point Q, -1 and 9, I can find the vector PQ by subtracting -1 minus 3. So it's important to be Q minus P coordinates. So -1 minus 3, comma 9 minus 6 to get -4, 3. If I want a QP vector, then we're going to have 3 minus -1, comma 6 minus 9. And that is going to give us 4, -3. Well, of course you are expecting the same vector in the opposite direction, because it's either P minus Q or Q minus P, right? P minus Q, Q minus P, depending on which way you want to look at this. So to find a vector given 2 points in space, let's say point P and point Q, you first need to know which way your vector needs to go, whether it's PQ or QP, and then whatever you have, just subtract the coordinates and you are done. Okay, good. Did I miss anything? Vector addition, that's done. Example, done. Vector components, that's done. Magnitude, that's done. Vector operations, addition, subtraction, scalar multiplication, all done. I need to talk more about the unit vector. I only mentioned the basic ones. Let's go. Hard's thinking, so let's talk about unit vectors. I should go like this: unit vectors. Yes, it's time to panic. Is it important? Oh, yeah. If you want to decompose vectors, if you want to find some directions and projections, and later on we'll have a unit tangent vector, that might be important, right? Principal unit to normal vector coming up next section, next chapter. These are all unit vectors. So far, I only talked about 2 unit vectors, which are basic direction unit vectors, I and j. First property of unit vector, Magnitude is always 1, hence the word unit. So I really get depressed when I ask at a test, compute the unit vector, and then it's just magnitude of that thing is 17 for some reason. Magnitude must be 1. Now, the direction of the vector is in the direction of the original vector. Direction, same as original vector. Formula, u with a hat. That's the notation for unit vector. Is you take your vector u and you divide by magnitude. You see, you're technically dividing a vector by its magnitude, so you're technically just taking away all of the quantity that it has, scaling it down to 1. And we are not messing with the direction at all. Let's take a look at an example. Say vector u is 6 and negative 2. What is the unit vector u hat? Well, u hat is going to be the original vector 6, negative 2 divided by the square root of 6 squared plus negative 2 squared, which is the magnitude. We still have our vector 6, negative 2 divided by the square root of 36 plus 4, that's 40. Which is that 2 root 10? 2 root 10. 2 root 10. And now we divide. You are getting a vector 3 over root 10 and negative 1 over root 10. Now we don't like root 10 in denominator, so u hat is going to be 3 root 10 over 10, comma, negative root 10 over 10. So this is your unit vector, and you can quickly show that the magnitude of it is 1. You know, let's say you care, right? You want to check. What do? You just find the magnitude, make sure it's 1. Check. I'm gonna go green on this one. I don't use green enough. So magnitude of u hat. Magnitude of u hat should be 1. We know how to find the magnitude. You take the coordinate, you square it, and then you add the square of the other coordinate. So root 10 squared is just 10, so this is 30 over 100. There's the square root. Plus 10 over 100. Your now, well, this doesn't work. Oh, 3 squared is 9. That's 90. Holy nightmare. Scared me. I thought I broke math. There we go. I forgot to square 3. It's time to go home, right? Everyone's, yeah. We had the 15 minutes of class. It's good enough. Let's go. Now, the direction, I promised that the direction of this unit vector is going to be the same as the original vector. So now we're going to find the direction. Direction theta is inverse tangent of y, which is negative root 10 over 10, divided by 3 root 10 over 10. A lot of stuff cancels over here. Root 10, 10, and 10. Tangent, inverse tangent is odd, so minus jumps outside. So I have negative inverse tangent, and then I have 1/3. You can get decimals if you love them so much. Now we're going to also look at the inverse tangent of the original vector for direction. Original vector is 6, negative 2, so that's negative 2 over 6. Negative jumps outside, you get tangent inverse, and again 1/3, same. So two requirements of a unit vector are to have magnitude of the unit vector to be 1, hence the name unit vector, and then the direction of the unit vector and the direction of the original vector has to be the same value. And obviously you must know the formula for unit vector, and I mentioned that you guys will be calculating later on unit tangent vector, so you will be figuring out that, and then you will use the derivative of that in some formula to figure out the principal unit normal vector and all of these things. So there is a lot of cool stuff there. Now at the end of this lecture, before we hit the break, I'm just going to put down 10 properties of vectors, and these will be the same for the next lecture. So I'm just going to say properties of vectors and put 2D and 3D in parentheses. Properties of vectors, I'll put 2D. You know what, I'm just going to say any dimension. Because these, you know, can you have a 7-dimensional vector? Yes. It's not a problem. Is it the thing? No, but, right? It's, we live in a 3-dimensional physical space. You can add dimension of time and so on, but we don't really have a 7-dimensional space. Mathematics, you can have any dimension you want. So what are the properties? Number 1, commutative property. U plus V is the same as V plus U. Number 2, associative property U plus V, in parentheses, these are all vectors, plus W is the same as U plus V plus W. Number 3, if you add a 0 vector, you get your original vector back. 0 vector is technically just the point at the origin, because 0 vector has no direction to it, because it has no components to calculate your arctangent, and also the magnitude of the 0 vector is 0, which means it has no length. So your 0 vector is in this case defined as 0, 0, which is just the point at the origin. Your 3D 0 vector will have 3 zeros in it. Property number 4, when you add vector to the negative of the same vector, you get a 0 vector. Followed by 2 distributive properties. That's 5 and 6. The first one is that the constant will distribute to both vectors. So we have Cu plus Cv. Or if you have 2 constants, C plus D times the vector U, it's going to be Cu plus Du. Guys, the arrows that I'm placing every time, and yes, it is annoying, are not there for decoration. The reason why I don't have to specify that C is a scalar, just a number, and U is a vector, is because C has no arrow above and U does. So on your exam, every time you miss an arrow, you completely miss a concept. Your textbook, instead of placing arrows, is using bold letters for vectors and non-bold vectors, non-bold characters for scalar quantities. So since you can't do, bold, well, you just put the arrows everywhere whenever you have a vector. 7, 0 times vector v is a 0 vector. Okay, this is amazing. You see a 0 without arrow and 0 with arrow, right? So 0 without arrow is just a 0 you know and love, and then 0 with the arrow is a 0 vector, which is this. So it's important. Now we have property 8. Constant times a 0 vector is still a 0 vector. Shocking, I know. Number 9, 1 times vector v is what?
Vector v.
Yeah, vector v. I just wasted my virtualing. A times C times vector v is, this is associative property for multiplication, ACV. The proofs for all of these are really, we don't focus on proofs, but the proofs for these are very, very easy. To show any one of these, you just, write vector component vx, vy, and then when you add 0 to each one of those, you get this one back. Over here, vx times 0 is 0, vy times 0 is 0, so you get 0, 0. Proofs are very, very easy for all of them. You just have to write each one of these vectors as ux, u, y, vx, vy, wx, wy, if you have it, and just keep distributing c's and d's and whatever is needed. And you can quickly come up with proofs for all of this. That's only if you're interested. So I think that's it. Oh, and then they have these cool physics problems that you can enjoy. I like talking about this problem actually because the angle at which you are pulling or pushing objects is important, especially if something is very heavy. So this chair rolls easily on this. Even if it was just concrete, it still will be easy, right? And imagine that this was a 1-ton block. Let's go with a half-a-ton block, like the ones they shoveled in Egypt, like this. The half-ton blocks, and then they stacked 2.2 million of them perfectly, so that at the apex of the pyramid, when you do the diagonal of the base, which is 6 football fields large, it's 1/4 of an inch off. Yeah, they had no crane, no pulley, no, right? Anyway, so try to find the right angle in your house with laser technology we have today. You're not going to find one because you put the triangle ruler, you put that in a corner, it will be wobbling, right? Pick any corner of your house. And they stock 2.2. So if this is a half a ton block that I'm supposed to now, just pick up and put it in place. If you push it this way, it's bad. Why? Why is it bad? Well, look at the angle of the attack. right? If I'm attacking at a 45-degree angle, this vector, which is going to take the force that pushes this, is decomposed into a vector that is going straight down up to this height, and then the one that goes forward. Am I going to bury this chair into the ground? So isn't all of this wasted? Yeah. You're attacking this chair at the cosine of 45, right? Cosine of 45, that's a root 2 over 2 factor scaling down the force with which you are attacking the object. And that's not good, right? You are wasting energy because the object is not getting buried, because the way the normal force works in physics, when you put your foot on the chair pushes back, and then those two forces equal out, and that's why you're all stationary right now. So, action, reaction. You push, the other thing pushes back with the same force. Right? So now, if I am pushing this chair, square root of 2 over 2, because I'm at 45 degrees, resting my arms, right? Or pick whatever. Square root of 2 over 2 of the force is pushing the floor, and the floor is pushing back, and all of that is wasted. You have to be at the level parallel to the ground so that 100% of the strength of the push pushes the object. That's when it's easiest. If you attack at any angle, well, it's perceived that it's easier, but it's immediately waste of energy for whatever angle you have, and you can compute those things very easily because now you know at the sine, cosine, you just compute what you need and you're done. So the stuff is really useful. Clearly, you can see mechanical engineering all over the place. More examples of these word problems for physics. You hang stuff. You have the tension in chains and tension. If you want to pull. Well, I think they're pulling the engine block out of the. Yeah, a 400-pound engine is suspended from two chains that are 60 degrees each, right? So all of these things can be easily computed. All you need to do is to decompose the force. You can see they're using cosine of 60 and sine of 60. And then sum of all, that's now physics. Sum of all forces in x direction has to equal to 0. Sum of all forces in y direction has to be equal to 0. And then you can compute the tension of the chain, which is actually the force of the chain. If the tension exceeds certain level, then the chain breaks. So you need to be careful about those things. And then you have a whole bunch of homework exercises to enjoy and practice. And that's that. So let's go for a break. And then we'll move to the 3D when you come back.